Hello everyone and welcome to another episode of Solving Advent of Code in Rust and try to learn Rust in between. I'm Roberto and we have...
Luciano, hello.
Thank you for following along. If you never did Advent of Code is a code challenge that is published every year in the Christmas period. We are working toward the last year one. There are 24 challenges and you can find them on adventofcode.com. You can see the chat for the link because today our overlay is not working. We are publishing all our code in a GitHub repository. That is again in the chat. And we have a YouTube channel where we publish all our recording. You can find the link in the description of the Twitch channel. We start with a thank you to WGAFA because he posted a pull request against the exercise from last time. That was 19 of year 2021. So thank you. And today we start with exercise 20 of 2021. For this one, we already have a pull request because Luciano did this probably around the Christmas last year, right, Luciano?
Yes. I don't remember at all what I did, but we'll try to figure it out.
Perfect. We will read the README and we'll find out what is about this exercise. Then we will show the Python solution and we compare it, and we will compare it with the Rust one. So, do you want to share your screen, my screen?
Let's go with your screen first. You have the README there, right?
Yeah, this is the README. Sorry, I'm scrolling up, down. Here, day 20, trench map. With the scanner full deployed, you remember that Advent of Code is this beautiful story that is somehow regarding Santa. This time Santa lost his keys in the trench. So we have to find the keys. When you get the image from the scanner that we put together last time, the scanners, last 3 times we put together the scanners, it seems random noise, and we need to use an enchantment algorithm. An enhancement, sorry, not enchantment.
Enchantment would have been nice, yeah.
Enhancement algorithm on the input image. That is our puzzle input.
Mm-hmm.
So we have this line. All of this is just one line. That is the enhancement algorithm. And this is our input image. The first section is the image enhancement algorithm. It is normally given as a single line and is made of light, sharp, and dark dot pixels. The image enhancement algorithm describes how to enhance an image by simultaneously converting all pixels in the image into an output pixel. Each pixel of the output image is determined by looking at a 3x3 square of pixels centered on the corresponding input pixel. Oh my God. So to determine the value of 510, we have to look around 510, 409, 410, 411, 59, 510, 511, 69, 610, 611. So based on this image, if we want to know how this point evolve, we have to look into these 9 points. So 3 in 3 lines that are 9 points. So the points itself. That will give us a binary number where a sharp is a 1 and a dot is a 0. We will get this binary number that is 34. At that point, we can with 9-bit, we can have a number between 0 and 511. So 512 numbers. That is the length of our enhancement algorithm string. At that point, we have to look in the corresponding point, doing the lookup in the string of that string. And if we find a sharp, the output will be a sharp. Otherwise, it will be a dot. So it will be a point of light or not. Through advancement in image technology, the images being operated are infinite in size. So remember, the image is infinite in size. This give me some problem at the beginning of this solution. Every pixel of an infinite output image needs to be calculated exactly based on the relevant pixels of the input image. So given the README example, we evolve like a game of life with strange rules, all of this, and then it's going on and on and on.
Yeah, and you can see that the image gets bigger in a way. It's kind of zooming in.
Yeah. Every time the image gets 1 pixel per side bigger at every step.
So this is basically the technology they always use in all those movies where they find the killer by a reflection in a glass, just by zooming in.
Yeah, the reflection in a screw on the plate of a car that was passing by at 8 kilometers per hour while a pigeon was flying in the wrong direction. Yeah, those kind of magic stuff. That AI is doing a lot of stuff, not at CSI level yet. Start with the original input image and apply the image enhancement algorithm twice. So part 1 is asking to apply it 2 times. Being careful to take in account the infinite size of the image, how many pixels are lit in the resulting image. Your output is 4017. I'm reading also part 2 because it's not very long. It's basically, you have done this twice, good. Do this 50 times now. After you do this 50 times, how many pixels are lit after 50 times?
So this is one of those exercises where it doesn't change the logic between part 1 or 2, it just changes the amount of times you need to repeat the algorithm. So probably it's pushing you to figure out an efficient way to solve the problem.
Yeah. One stuff that I wanted to show is that when that is the stuff that I took a while to understand of this problem, is that if we go in a point in the infinite space that we have, obviously we will have a 0 as index of this of any point that is outside. Any point outside, obviously surrounded by nothing, is nothing, so it will be a 0. If we go in the README and we look at the enhancement algorithm 0 of 0, so the first charter, it stays not lit, it stays dark. So something in the dark outside is still dark. Easy, but in the input is different. Index 0 of our input is lit in all the inputs probably, because this is the trick of this exercise. Being that lit, what happened? It happened that every time that there is an iteration,
you expand basically, right?
All the plane of infinite points becomes full of lit points. And at the next iteration, obviously the last one at that point will be in our input again off. Yeah. Every time the even iteration, you will have all the points that go back to off. I can show you this in a Python. This is my input in Python. The circles that are here are the lit point, the one that are on. After the first iteration, what happened? All the infinite space around it now is lit. And the other points inside change based on rules, right? Then what happened at the next step again? The rules say that when something is lit, surrounded by stuff that are lit, it turns off. So the infinite space around it turns off. And one iteration yes and one no, the infinite rest of the space is lit or not. Obviously, I was not representing the infinite amount of points that are in the infinite plane, because obviously you can't. I was just keeping, the trick is to keep a counter of which step are you in, and if I'm in an odd step, the infinite space is lit. If I'm in an even step, the infinite space is turned off. So this is just how I did in Python. I don't know what to do.
And I suppose that you have like a bounding space, right? You never compute, you never draw more than this bounding space, right?
Here in this visualization, yes, I have fixed between -50 and 100 and 150. Why? Because the input is 100 by 100. We are doing 50 iteration. So at every iteration, we get 1 pixel in any direction bigger. So we can only go to -50 to 150, because starting with our first pixel in 0, 0, there is a convention because the space is infinite. So the first pixel can be 100, 100, 50, 50, 1, 1, 2, 2. I don't care. Just keep the stuff relatively, because they ask us for the number of lit points, not for the position of them. So there is no problem. So the visualizations, as you can see, when we arrive at the end of all this.
And by the way, you can see that the space keeps growing.
Yeah, keeps growing by 1 at every iteration. You will come out with a bunch of points that you have to count them. So do we want to see the Python solution? Probably yes, because we are here. So part 1.
Can you make it like 1 point bigger? Thank you.
Was 1 enough or more? This is enough? Okay.
Good for me, at least. If anyone in the chat prefers to zoom more, let us know.
Tell us something, yeah. I solved this with Numba. Numba provides you a just-in-time compiler for Python, because obviously working with bare numbers in Python is slow. So doing this, I'm getting better performances. And all of this is just numbers. So there is no...
So it's basically compiling like in C? As it goes through the code?
I think it's inferring the types, and I don't know internally what it's doing, if it's using NumPy. I think it's doing some tricks with NumPy under the hood, so the NumPy is written in C, so in the end you're using APIs. But I'm not exactly sure how now Numba does this magic. But in the end, the parts of the input, I'm keeping the input already pre-parsed, enhancement, string, and image. So the parts of the image is creating a grid that is a dictionary. I used the dictionary to take in account the infinite space, but this could also have been a set with just the delete point in it. I kept a grid and I was putting sharp or dot in the grid, 0, 1 in the grid, if it was on or off. In the end, performance-wise, there is not a big difference in this. So for every line, for every row, grid of x, y is equal to 1 if the character is a sharp. Otherwise, it's a 0. So the parser is, we already saw this parser 1 million times. pprint is a function to just print the grid that for debugging purposes. Okay, the core of our solution is the step function. Step function takes a grid that is our dictionary of iterables that are 2 coordinates that points to a string. Default is if the infinite space outside around you is on or off. I call it default. Then I'm taking the minimum x, the maximum x, the minimum y, the maximum y to know where from start and end of my grid of points, because that will change through time. I'm creating a new grid, that again is another dictionary. Now I'm going from the minus x minus 2, because we have minus x that is here. We have to evaluate the minus 1. Why I'm doing minus 2 and not minus 1? It's not important because it works. But in any case, I probably could have done minus 1 and plus 2 and not minus 2 and plus 3. In any case, I'm taking a little bit more space around the current number of points that I have. I'm creating my binary number that starts as a 0. Then for minus 1, so the 1 on the top right, top left, top right, left, center, right, bottom left, bottom center, and bottom right. So all the possible permutation, movement from the center. I multiply the number by 2 because it's a binary, so I shift by 1 bit and I push the new bit in. If there is no point in the map, if there is no point in the dictionary, I'm taking default as a value that will tell me if I'm looking in the infinite space outside that is lit or off, depending on the iteration. Then at this point, the new point based on the enhancement, not enhancement. Why enhancement?
Well, it's a bit of an enchantment because it's
on the enhancement string. I look if it is a sharp or not. I put a 0 or 1. Then I do this. For part 1, I do this twice. Parsing the input. First step. Second step. Give me the number of points that are lit. My input is different from yours, so I have a slightly different output, obviously. And this is part 1. This is also part 2, because part 2, guys, is not...
it's just doing different. It 50 times, right?
Yeah. For I in range of 50, do this, and then give me the answer. Even with the... this is without the just-in-time compilation, because you notice there is no Numba here. So without Numba, it takes 4 seconds. Okay? With Numba, so all we did was adding this. Nothing else. We didn't change our code at all. We added this and this on top of as a decorator of the 2 functions that we declared. We did nothing else, and we went from 4 seconds to 0.9.
Nice.
So 4 times faster is a good gain for an interpreted language like Python. Then this is the graph that the plot, the animation that I already showed you. Then I think there is a bonus track. I did this also with the GPU, because on Colab you can ask for a runtime with GPU, and Numba has CUDA, that is an NVIDIA technology, and you can use the GPU to solve the problem. This is an image, it's a problem tailored for running on GPUs. And what I did, I had to change a little bit how I parse everything. Now I have NumPy arrays, bidimensional instead of dictionary. I know that I will have at most 200 by 200, and I start allocating my input starting in 50-50 and not in 0-0, so I don't have to handle negative indexes. So I'm a little bit cheating here. But you can do this without hardcoding, with parameters, parsing the input before and getting these parameters out of the input, because this is just size of the input, plus 2 times the number of steps that you have to do. So, and this is the number of steps you have to do. So step is doing the same. New grid for all the numbers in the grid, take them to the iteration and set the new point. Same exact as before. Doing this with GPU step, that is basically am I allocating one worker in the GPU for every point. So every time there is a step, I allocate one worker for any point in the 200 by 200, and I am running the kernel, because this is called kernel when it runs in a GPU. I'm running it in this worker. So I spawn a lot of workers, because there are 400,000 workers that will be handled by CUDA, so I don't care. I give them the grid, the new grid, because CUDA can't, a GPU kernel can't in CUDA return any value. They can only modify arrays that you pass to them. They can't return an array. You have to pass the array, and they will work on that array. I'm also passing to the GPU the enhancement string, that is again an NumPy from ITER. And I'm passing the default to tell if we are in the infinite or not space. All of these are arrays that are created in the memory of the device. The device is the GPU. So those arrays are not in Python. Those arrays are referenced by Python variables, but they are in the GPU. So long story short, after all of this, the algorithm is more or less the same. It only has to use NumPy arrays instead of dictionaries. We went from, I don't know, because why here the part 2 JITted was faster than 0.9, was 0.14, but we went down with the GPU to 0.01. So from the 4 seconds we started with, we drilled down to a 1 cent of a second.
Nice. The one thing I don't understand is you only need, in this part where you use CUDA, what is CUDA to device actually doing?
This one is transferring memory from Python, from this Python that is running in the CPU, to the memory of the GPU.
Okay. And then how do you work on that memory with the GPU step function?
With the GPU step function, that note that it has this strange way of being called with these square brackets that tell to the GPU how many blocks and threads to allocate. Blocks and threads are concept in a GPU in CUDA. Because threads can share memory between them, blocks don't share memory between them. But here there is no memory to share internally between the threads. There is all stuff about thread synchronization, of threads. CUDA is the Python interface is simplifying a lot of stuff, but there are concepts that you have to digest before using it. So those are stuff that I create in Python, then I have to send to the GPU, because the input comes from Python, because it comes from their drive. I have to load them, parse them, send them to the GPU. Then I have to use them in the GPU. And then at one point I have to transfer them back. But to transfer them back, CUDA is doing that for you transparently. So when I access grid here, is transferring back the array from the GPU to the CPU, and at that point I can do math, or normal math with NumPy or with Python on top of that array.
So the first time I wrote. Sorry, the only step you are running there with CUDA is only the image enhancement step, right? Everything else is just regular Python.
Everything is normal Python. The only function is this function that takes a array that must be in the device memory. It writes in an array that must be in the device memory. It takes also an array that must be in the device memory, and is taking an integer. Probably this is just transferred, because here I didn't told CUDA is transferring that to the device, to the GPU for you. CUDA in theory is doing all of this for free normally for you. My problem is that I had to handle that manually, because at every iteration I swap the 2 buffers, because the new image is the old image, and then we go on like this. So I only have 2 buffers. And if I was not doing that, every time I was swapping the buffers, Python, CUDA, NumPy and CUDA were downloading the memory from the GPU to the CPU, swapping the memory, and then uploading the memory again. That was useless. And when I was doing that, it was taking me 24 seconds to run everything. And it was like, how is it possible that with the GPU I'm taking 24 seconds and with the CPU I'm taking 4? Because I was doing the handling of the memory transfer in a bad way. It was my fault. So now, what you did in Rust?
Yeah, let's have a look. Let's try to remember, because I haven't reviewed this one. So last time I looked at this one was like 8 months ago or something, or maybe 9. So
swap the screens.
Yes, just a sec. Swap the screen. Okay, should be swapped now.
Yeah.
Cool. So here I'm going to actually show the eye level first, and then we're going to zoom in to the different components. So part one is very simple. So we have we split the input by the two empty lines, and we get the two raw parts. Well, I always get confused with IEA is the image enhancement algorithm, and then there is the image part. So they are just collected as two strings. Then I have two different types of structs, one for IEA. And one for
you can change the name when you want. You can change the name when you want.
Exactly. And then I have just an image. And then I can parse both. So I actually have structs that I can work with. And then basically every image has the enhance method, which is just going to do an iteration and give me back a new image. So in the first part one, I'm basically just doing that twice. And then I have a count light pixels method and just returning that. So at the very high level is very simple. And the difference between part one and part two is that here I'm just doing it twice, like just copy paste. And here I'm doing a for loop 50 times and then calling the count. So all of that is pretty simple. Now let's try to zoom in into, for instance, how do we do this raw IEA parse?
So first of all, what is IEA? Okay, it's a Nash set of view sides.
Yeah,
why a Nash set?
A Nash set of view sides because basically, what am I doing here? Let's see.
You're only keeping the numbers that are sharp.
Oh yes, I think so. Yeah.
So you will have a set with numbers between 0 and 511, but obviously not all of them, some of them.
Yeah, and you can see here that there is a method isLight. It's basically just checking if you have that value in the set.
Okay. Instead, I kept the string as a string, and I was doing a lookup in the string.
And then the parse is pretty simple. It's basically just doing an iterator over the string. And then for every char, every time it's doing an enumerate. So every time that the char is an hash, it's just adding it to the set, basically. It's just adding the I to the set. And that's it. I think
so you will have this set of integer of view size, sorry.
Yeah, this struct is basically a wrapper around the set, and it gives me a few additional methods. Actually, only one method, which is isLight of a given position. Maybe this should have been called isLit, but whatever.
But well, it's fine.
Okay, then the next thing is how do we represent images? Let's see, because I don't remember, but it's a struct with many properties. So we have min row, min column, max column. So I have like a bounding box with these 4 properties, and they are I sizes, so they can also be negative. Then this default, I don't remember what it is. But it's
look, probably will be the same as my default, but let's see.
And then I have pixels, which is, again, as you did, I am keeping an hash set of only the lit pixels, and I'm keeping the coordinates, basically.
Yeah, I did additionally, I could have done a set, but lazy me. And instead, I'm computing min, max every time. Instead, you are probably updating it. From that point of view, yours is faster because you are keeping that computed instead of recomputing at every step. Cool.
Okay, then we also have a parse for the image. So we have to basically read all the stuff here and convert it to an image struct. So what that does is basically it's creating the hash set for the lit pixels. It's initially starting with max row and max column to 0. Then as we keep going, we have for every row and for every column, every time we find a new row, we increase max row and we put max column to 0. And then inside this one, is basically for every column, we increase max column. And then if the column, if C, which is the current character in this string, so every time we find a sharp here going line by line, column by column, what we do is basically we say pixel.insert. Pixels is basically the asset. So we add into that hash set the current row ID and column ID. Does that make sense?
Okay. Yeah. I don't know why you reset max call and then you update it in every row.
Yeah.
Because in the end, the row are they have always the same width.
Yeah, exactly. It feels a bit unnecessary.
And the max row is the length of that. Okay, max row is fine because it's a counter.
Yeah, I'm not even doing like an if statement. So I'm just assuming that the last column is...
you take the length of the last...
last cell, which is going to be the maximum column anyway.
Yeah, okay. Yeah, because it's a square. But fine, it's working.
So yeah, it's not the prettiest.
Work.
Yeah.
No, it's a little bit of extra work, but it's an integer, so who cares?
Yeah, to be honest, I could have done max call equal the size of a row, like the first.
Yeah,
item.
The size of the first row, if there is one, and the max row is the size of the S lines. That probably you can have it somehow. But yeah, again, who cares?
Okay, then at this point, I think we have everything because we have pixels, which is the hash set with all the ones that are lit.
Yeah, the mean start at 0.
Exactly, and then max column and max row, which are the ones we found here while going through the data, and default is false, still to be figured out what default means. Now, let's see the implementation of
I have a feeling.
Okay, so we have a couple of methods, I think, enhance pixel and enhance and count light pixels. So we actually have 2 methods for enhancement. And
which one are you calling from part 1? You are calling enhance?
So enhance pixel only returns a Boolean. So I think it's more, you give me just 1 point and 1 EAA.
Okay, so let's start
Tell me what's going to be the final status. So this one is more high level, the enhance.
Yeah, but our part 1 is jumping in enhance. No, it's not
exactly. Yeah. So this one is more higher level. So what do we do? Basically, we say take the current image and enhance it using this particular algorithm. By reference, it's going to return an entirely new image. So basically, at every step, we compute an entire new image and we can discard the previous one. So what do we do here? We say, let's start by creating a new hash set of pixels. Initially, it's entirely empty. Then min row is basically growing by 1 on the negative side.
On the left, yeah.
Max row is growing on the right by 1. Min column is growing by going
up. Row are growing up and down. It's column that is growing left and right, but okay. They are growing.
Oh, yeah, you're right. Column left and right, row going up and down.
And down, yeah.
So it's like you are adding a new border of 1 pixel all around the previous image, pretty much.
Yeah.
Then what do we do? It's basically for row ID in min row, max row. So basically for every single row in the new image, and then for every single column of the new image, if self-enhance pixel of this coordinate, ice cream time.
Yeah.
Yeah, this is the background music from Roberto, who has the ice cream van passing by his window.
Sorry.
It's pretty cool. Okay, sorry. So what we are doing here is, again, for every single coordinate in the new image, we call this other function enhance pixel. And then if this function returns true, then it means that the pixel is lit in the new image. So we set that value. We do all of that. That means that basically we iterate over every single cell. Then at that point, what do we do? Default.
Yeah, you create a 9x9, a 3x3, so 9 array of default. So the current value of the infinite space. You make it a number. So with that byte bit shift, you make it a number, and you sum it together. So you will have the number.
Yeah.
And
so
then
this will be a usides.
Yeah. The next default is the projection with the enhancement algorithm. So looking if it's lit or not. Of the current default. The infinite space is, you turn on and off the infinite space again, doing the lookup in the enhancement algorithm image, line, string, whatever.
Yeah. So yeah, this is the default.
So the default in your exercise is exactly the default of mine. And we didn't talk together to solve this. So, yay.
Yeah, great minds.
Yeah, things
or bad minds think alike. Hey, hello, Braum, how are you?
Yeah, in the chat. What is this name? Braum, the nutty digital artist. Net one. Oh, hi.
Welcome to the chat. How are you doing today?
I hope I didn't slaughter your name too much.
Okay, so the last thing that we need to observe is how do we do this enhance pixel, right?
Yeah.
So let's have a look. So enhance pixel takes the current reference to the image, so has access to all the pixels of the image, then the row ID and the column ID of the current pixel that we want to enhance, and then the image enhancement algorithm reference. And it returns a Boolean, which basically means true if it's going to be lit, false if it's not going to be lit. So what do? We set a variable I that initially is 0. Then we have values, which is a Boolean of 9 items, so all the positions around the current pixel and the current pixel included. They are all initially false. Then what do? Delta row. So it goes from -1 to 1, and then delta column -1 to 1. So basically, I'm calculating all the relative positions around the pixel.
In the Python one, I just hard-coded them.
Okay.
You were lazier.
Probably yes. Probably your solution is faster because here I'm recomputing all the coordinates all the time. If you had
those
like
are integers, I think there is not a lot of difference.
Yeah, probably it's not relevant. Anyway, we calculate effectively all these 9 cells, and then at this point here, this is where the logic starts.
That is a boundary check. Yeah.
This is a boundary check if I am still inside, because of course you can have like corners or border pixels, and in that case you shouldn't be looking outside, right?
Yeah.
So in that case, if you're looking outside, the value that you take is the default one.
Is the default.
If you are looking inside the image, then you actually check the value of the image, and it is lit only if self pixels contains that particular coordinate. And then at the end, we do I plus 1. Why do I do this?
Yeah, because we are populating the Vals array. So you have done the first bit, then you go on and you do the second bit. Because 3 by 3 is 9.
Oh, yes. So this is just allowing me to
loops are
keep
3
value,
because minus 1 to 1, including 1 is 3. So the loop is 3. 3 by 3 is 9. So your index on your array must be between 0 and 8, included 8. That are 9 numbers.
Yeah, basically I is the index over vals as I populate vals.
Yeah. So and when you have these 9 bits, now what are booleans? Yeah.
They are booleans, and again I do like a compute a number out of that, and then I check is light.
Of that
compute a number is basically bit shifting to create a usize.
Yeah, you take every boolean and you cast it at usize and you bit shift by its position.
Yep. In reverse.
In reverse, yes, because we are doing big endian.
So Braum is introducing himself. People just call me Braum. I'm new with programming. I decided yesterday to learn Python instead of Java and JavaScript. Good choice, especially not Java, to Python or JavaScript. What we are doing today, because I think you just joined, is we did a little bit of Python. We are solving Advent of Code, which is a challenge that you can find on adventofcode.com. We are solving all the exercises from last year in our streams, and we generally do them in Python first, and then we compare that with Rust, because we are trying to learn Rust as well. So even if we are a little bit more experienced programmers, we are always learning, and this stream is something we do to actually keep learning new stuff. So feel free to ask any questions, and we'll try to answer. Okay, so that's everything, right? Is there anything else we need to see?
No, question. You have benchmarks for this?
We do have benchmarks, yes.
Just out of curiosity, what is the speed in release?
Yes, so I think if we run the benchmarks, they run.
I think a Cargo bench is running in release mode. Yeah.
Yes, so CD year 2021, exercise 20, Cargo bench. Let's see what's the speed. So this might take a little bit to compile because I updated my Rust.
Yeah, there was a meme, the other day about a guy crying and written, when a developer compiling in Rust, see his power bill.
Yes, my CPU is like 80% right now. Now 100%.
Yeah, compiling, take his time and this price in a megawatt.
Okay, so it's running the benchmarks. By the way, so what Python, these benchmarks? Go ahead, Roberto.
Python, you are still faster than the GPU. Incredible. No, this was part 1. Sorry.
Well, let's see. Part 2 might be a little bit slower.
Part 2 in Python was 4 seconds, the normal solution, 0.9, the JITted one, and then 0.01, the GPU one.
Let's see here.
Part 1, I didn't did any benchmark because with only 2 loops, they are not enough to really stress the machine. Thank you for the subscription. Following, sorry, not subscription.
Thank you, So this was 400 milliseconds.
Second, 400 milliseconds. That is still double as fast as the JITted Python.
Which makes sense because I suppose the JITted Python needs to run a little bit slow to figure out all the types, and then it needs to spend the time compiling in real time, and then it gets faster, right?
Yeah, so it has overhead, obviously. Probably running that multiple times, the average goes down because the first JITting, the first compilation get how you say, basically it's paying back in the next runs.
Yeah.
The GPU instead is still faster because
it's optimized for this kind of operations.
Yeah, because if you spawn one worker for every point of the image and you do them all in parallel, obviously you're faster. Even if in reality your GPU doesn't have all those workers, but CUDA is putting down a queue on its own and you don't have to think about it.
So what do we do next? Do we just merge our Rust.PR? Do we want to look at the next exercise?
I think we can merge if you are fine, and we can jump in exercise 21, and I can show the Python solution for it. So we can read the README and then showing the Python solution.
Let me go to this PR. This is our repository where we keep all the solutions, so we can merge this one. And
I did some improvement. I did some improvement in the flame graph.
Nice.
GitHub Actions. I'm not sure it's working anymore, but at least it's faster.
Okay, nice. We'll test it better.
Next pull request that somebody will open, or we will open, I will check if the flame graph is running, but it's not preventing the merge. It's creating an artifact that is kept for 5 days in the GitHub Actions, and that has an SVG with the flame graph of the exercise.
Okay, so I'm gonna read this one. So basically, what are we doing here? This is another day, another challenge to try to find the key that we lost in this story. And basically, we are descending to the bottom of the ocean, and the submarine computer challenges to a game of Dirac or Dirac dice. The game consists of a single die, 2 pawns, and a game board with a circular track containing 10 spaces marked 1 through 10, clockwise. Each player's starting space is chosen randomly, your puzzle input. Player 1 goes first. So effectively, this will be a game where there are different things happening, and you'll need to simulate the game state. And probably at the end, we'll need to return a value that depends on the correct simulation of the game. So players take turns moving. On each player's turn, the player rolls the die 3 times and adds up the 3 results. Then the player moves their pawn that many times forward around the track. That is, moving clockwise on spaces in order of increasing value, wrapping back around to 1 after 10. So basically, there are 10 cells circular. You move around these 10 cells, and if you get to the 10th one, the next one is 1 again.
Yeah, it's circular.
So if a player is on space 7 and they roll 2, 2, and 1, that means that basically they have to move by 5 times to space 8, 9, 10, 1, and finally stopping on 2. So pretty much as any other, like if you play Monopoly, it's the same idea, right? You have a board that goes around all the time, and if you get to the end, you continue to the first step. After each player moves, they increase their score by the value of the space their pawn stopped on. Player score starts at 0. So if the first player starts on space 7 and rolls a total of 5, they will stop on space 2. So they have to add 2 to their final score, so to their current score. The game immediately ends as a win for any player whose score reaches at least 1,000. Since the first game is a practice game, the submarine opens a compartment labeled deterministic dice, and a 100-sided die falls out. This die always rolls 1 first, then 2, then 3, and so on up to 100, after which it starts over at 1 again. Okay, play using this die. For example, given the starting position, player 1 starts at position 4, player 2 starts at position 8. This is how the game will go. Player 1 rolls 1, 2, 3 and moves to space 10 for a total score of 10. Player 2 rolls 4, 5, 6 and moves to a space 3 for a total score of 3. So you can see that the dice always rolls the next number every time you roll it. And every player needs to roll it 3 times and simulate the move. So eventually one player will get to 1,000 of score and they will win. So what is the question? Play a practice game using the deterministic 100-sided die. The moment either player wins, what do you get if you multiply the score of the losing player by the number of times that the die was rolled during the game? Make sense?
Yeah.
Should we read part 2 or?
No, part 2 is quite different.
Okay, then should we just see the Python solution for part 1 and the Rust for part 1?
Yes.
I'm gonna switch the
screen.
They
are
to you.
Quite different. Yeah.
Are you ready to switch screen?
Yeah, I'm on the right window.
Okay, you are on.
Okay, so this is part 1. My starting position were 9 and 3. This is my parsing, so I wrote it. This is not a great parser function, but it's working. Basically, we have 2 integers as input of our exercise. Part 1, player 1 starts at the point. I make this simplification. the cells in circular go from 1 to 10. I made them go from 0 to 9. In this way, they were zero-based. Obviously, every time I have to update the score, I have to update the score with a +1, because the cell I'm on will be lower by 1 than the real value. Why I did this? To make easier to do the rollover. I did the rollover just with a modulo operation. So I start at the player start -1 because of this. Player 2 start -1. The score are both 0. And the die is on the 1 because it starts on 1. Then while it's true, so while I'm playing, then I will break if somebody wins.
Okay.
I go on and I say, okay, player 1 goes on 3 times the die +3, because if you sum 1, 2, and 3, is where you go. It goes 6. If you are on 4 and you sum 4, 5, and 6, is 4 times 4, 3 times 4 +3, and so on. So here I'm rolling the die 3 times.
That's a smart simplification. I mean, makes it probably slightly more efficient by using smart maths. I don't think I did that. I think I dumbly simulated everything.
I did the modulo because going 0 to 9, if I do modulo 10, I will be on the right final cell. I update my score, saying that my score is whatever it is, +1, because again, I lowered all the cells by 1. I put the die on the next face, that will be the die +3. If player 1 score is greater than 1000, the loser is player 2, so I will give back my losing score as 2, and I break the loop. Instead, if player 1 is not winning, it means that we can play player 2. Player 2 does the same. It rolls the die, it moves, it sums. Now, my R is S2. I don't know why I do this. Probably this is not needed. I don't see why this would be needed. Yeah, this is useless, but okay. I put the die on the new face. If player 2 is the winner, the loser is player 1 with the score of player 1, and I break. Out of the loop, they want they multiply the score of the loser by the number of times the die was rolled. Yeah, I think so. That is the -1, because it starts on 1, but it didn't get rolled to go to 1, so we have to remove 1. Now, I did exactly the same, so this is exactly the same code. I changed nothing, with just the, again, numba and JIT decorator. So those two functions are the same function, except for the decorator. And I'm comparing the times. So the result is the same, luckily, because it means that it works. And part 1, pure Python, takes 2.2 seconds to do 10,000 times the game. Part 1, with the just-in-time compilation, takes 0.01 seconds to do the 10,000 simulations. So again, JIT is faster. This time not only by 4, but this time by 200 times faster, more or less. Because this is absolutely a completely numeric problem. There is no arrays to move. Those are just integers that get manipulated. So doing this in Python is not smart. I mean, it's not Python the language to work with numbers at this level. But once you do the JIT version of it, it's instead quite fast. And the code is the same. You can prototype your code in Python, make sure it works. When it works, you just make it faster, adding 1 line. And instead, what you did in Rust?
Let's switch and let's try to compare the differences. Okay, so this is my part 1. I'm going to start again from the high level, and then we'll zoom in on the different things. And basically the input, because I don't think we show that, looks like this, which is literally text. Player 1 starting position is this one, player 2 starting position is this one. So basically the only 2 things that we care about is this value and this value, and we know the first one is for player 1, the second one is for player 2. Now, I was a little bit lazy here. I could have implemented a parse method somewhere and just do it that way. Instead, I copy-pasted the same code basically twice. I get all the lines from the input file, and then I take the first line with next. I split at the column, and then I take the second item, and then I parse it to usides. That's it, pretty much.
With 1,000 unwraps, yeah.
Yeah, so this could have been nicer if we did it like in a parse method. We could have done like player 1 and player 2 by just calling
You were less lazy than me because I just put the numbers in a variable.
Yeah. Okay, so we will do some refactoring if we have extra time, but for now should be clear enough what we are doing here. So first line gets a number, second line gets a number. First number is position of player 1, second number is position of player 2. Then at this point, we need to initialize the 2 players, player 1 and player 2. I have a struct called player that we will see in a second. And basically the only thing that you need to give it is the position of the player. And because my position is 0 based, for whatever reason, I am decreasing that by 1.
Luciano, I'm seeing an ad on Twitch. I don't know if
then we need
stop
to
for a moment.
Let's wait for the ad to finish. Good catch.
It's finished.
So I still see ad in progress for 40 seconds. So maybe let's wait for a few seconds.
Okay. Yeah. Cool.
So meanwhile, if people are seeing
you have the power.
Yes. If people are seeing us live right now, feel free to ask questions and we'll try to answer any question. Ten seconds.
Ready?
Almost.
Okay,
back from the ads. Sorry, everyone. We didn't realize there were ads going on, but going back to our stream, what we were doing, we're just looking at the parsing. So we parse the position of the player. Then we have 2 structs. We have a player struct, and we initialize 2 players by passing the position of each one of them. And
you're doing -1 too.
I'm doing -1 because I keep the position 0 based, while in the input is starting from 1.
It's 1 based, yeah. I did the same.
Then I also have another struct, which is called deterministic die, and I initialize another one. Notice how all these structs are mutable. And I also keep a reference, actually 2 references to current player and other player. So I have like a pointer to player 1 initially and player 2 for
because
player.
You swap them.
And then I can swap them and then use an arbitrary reference to a player to do 1 round of simulation. Then I do a loop, which is in Rust is exactly the same as your while true. So this is never going to exit unless you break. And what do we do here is basically we do current player.play and we need to pass the die. So this is literally just mutating the state of a player by using the current state of the die. And then if the current player has won part 1, so there is a function in the player that tells me, is this player a winner at this point for the rules defined in part 1? If that's true, we basically return, which means we're going to complete this entire simulation. And the value that we return is the number of rolls. So you can see already that a die has number of rolls in its state, and a player has a score in its own state. So we take the other player, which is the losing one, multiply their score with the number of rolls of the die. And then this memory swap, it's actually something pretty cool, which basically allows you to swap the 2 pointers. So current player becomes the other player and vice versa.
But it's not moving the data, it's just moving the references.
It's just moving the reference. And you can do this because the 2 types are pretty much the same. They are both pointers.
And the type player, what is?
So let's look at the type player and the type deterministic die. So a player is basically a struct, and the only 2 values that contains is the position on the board and the score. And then there are a bunch of utility methods. So there is new player, which is just initialize a player with a certain position and score 0. Then there is play, which does a simulation with the die. We'll see this in a second. I'm not sure if this is needed for part 2, probably, so I'm going to skip it for now. And then you have as1 part 1 and as1 part 2. For now, let's just focus on this one, as1 only if the score is equal or above 1000. Now, before looking at play, I want to look at the die first. So a deterministic die is another struct, has only 2 fields. Current is the current value. So it means you already rolled it and it has a specific value. And then numerals is how many times have you been rolling it. There are helper functions. When you initialize it, current is 0 and numerals is 0. Now, whenever you roll it, this is actually pretty simple. It's basically checking, is my value 100? Because if my value is 100, the next value is 1. So this is kind of the boundary check. Otherwise, the current value is basically the previous value plus 1. And then every time you roll the die, it's just increasing the number of rolls. And then it returns the current value. Then there is another utility function that is, you can roll it 3 times, and it basically calls itself roll for 3 times and returns the 3 value in a tuple. Now back to the player. Rolls is basically calling rolls 3. So you get 3 values here. The total is the sum of rolls 0, 1, and 2. And then new position is basically the current position of the player plus the total modulo 10. And the score is whatever is the new position we end up with. We need to do plus one because we need to remember that all the points are calculated on the one-based system.
And we moved everything to base 0 to be able to do the modulo.
Exactly. And I think this is something where I spent a little bit of time making sure I got it right. I didn't realize immediately that I needed to do this. But anyway, finally we reset the position to the new position, and that's pretty much it. I don't think we need to see anything else there. We can run the tests if we are curious. So I have also a few examples, but this is the one we want to run. And it seems to work.
Cool. So let's read the part 2 README. That is a little bit more complicated.
Read part 2 README. Okay, part 2 is here. Now that we are warmed up, it's time to play the real game. A second compartment opens, this time labeled Dirac dice. Out of it, it falls a single 3-sided die. As you experiment with the die, you feel a little strange. An informational brochure in the compartment explains that this is a quantum die. When you roll it, the universe splits into multiple copies. One copy for each possible outcome of the die. In this case, rolling the die always splits the universe into 3 copies. One where the outcome was 1, another one where it was 2, and another one where it was 3. The game is played the same as before, although to prevent things from getting too far out of hand, the game now ends when either player's score reaches at least 21. Using the same starting position as in the example above, player 1 wins in this number of universes, while player 2 merely wins in this number of universes.
The problem is less, but I'm not going to compare them.
Using your given starting position, determine every possible outcome. Find the player that wins in more universes. In how many universes does that player win? So that means that we need to repeat the game how many times?
We have a starting universe. We roll. The starting universe
splits in 3.
Every time the die is rolled. Then remember that we have to roll it 3 times for every player.
So for every round, we generate 9 parallel universes.
No, we generate 27 parallel universes.
Why 27? Oh, yeah, because it's 3. Yeah, you multiply for every roll, basically. Yeah.
I think it's 27 at every. So you multiply by a lot. And in every universe, player 1 and player 2 will have a different number of, or probably even more than 27 now that I think about it. No, from a single universe. So you have to do this for all the universes. This become a lot of universes.
So basically, you stop going on when a match finish, and eventually all the matches will finish.
Yeah, because all the matches will arrive to at least 21. When a universe goes to 21, it disappears, and you know which one won, player 1 or player 2. Right?
Yeah, exactly.
At that point, you just update your counter saying, okay, player 1 won, player 2 won, and you go on until you run out of universes, because there will be somebody that won in all of them. In all gazillion, I don't know that number, how big it is 1,000, billions, trillions, a lot.
Should we check the Python solution?
Yeah. So Python part 2. Again, the start is the same as before. I'm creating games. Games is my universe. It is a tuple of 5 integers. What are those 5 integers? Position of player 1, score of player 1, position of player 2, score of player 2. Oops. And in how many universe are we in this configuration? Because I'm not keeping this list growing to that number, because it will not fit in memory. It would not fit in memory if I have to keep this state for all the universe that we are going to generate. So I'm only keeping a counter that tells me in how many universe player 1 and player 2 are in a specific configuration.
Right.
Then I have my Dirac dice that can roll. It will roll a 3, because if you roll it 3 times, it will roll a 3 only in one universe. There will be 4 universes in which it rolled a 4, because it can be 1, 1, 2, 2, 1, 1, and 1, 2, 1. Then there will be 6 universes in which he rolled a 5, because it can be 1, 2, 1, 2, 2, 1, and so on. Then there will be 7 universe in which he rolled a 6. Then there will be again 6 universe where he rolled a 7. There will be 3 universe where he rolled an 8, and 1 universe in which he rolled a 1. This is a Gaussian curve, now, just to say something new. And this is my die. Now, while there are games, so my games start with 1 element in it. While there are games, I create a new games list. For all the game in the games, I take out my 5 values from there. Then I start playing. I take my possible outcomes, that there will be 1, 2, 3, 4, 5, 6, 7 possible outcomes. And I say, okay, player 1 goes in this position, modulo 10, score plus the position plus 1, like we did in part 1. If the new score is greater than 21, it means that player 1 is winning in how many universes winning? Is winning in all the universe we come from, so he's winning in our universe count, multiplied by the weight. The weight is this second number, that is in how many universe this is going to happen. If this is going to happen in 7 universe and we come from 200 universe that were in this configuration, it means that player 1 is winning in 200 by 7 universe, and we updated the win player 1 counter that keep track of how many universe are is player 1 winning in. If player 1 is not winning, it means that we can try to see if player 2 is winning. So we do the same for player 2. This is exactly the same code. Now, if player 2 is winning, we update the counter that say how many universes the player 2 winning in. If this is not happening, if no players won, we add to the new games a universe with the new position of player 1, the new position of player 2, the new scores, and the new universe count multiplied by the 2 weights, so the probability of rolling a 3 and then a 6, or a 4 then a 7, and so on. After all of this, so after 1 round of player 1 and player 2, the number of universe will be way more. And I think there will be 49 more, probably, because they could be 7 by 7. They will be a lot more. I set new games to be games, and I go on like this until I run out of games. At the end, I retard the max between player 1 and player 2. That is what we want to know. Cool.
I think I did something very similar. While you were going through your code, I was reviewing mine, and it looks very similar.
All of this, copy and paste, with only this decorator on top of it, so no other changes again. We have the same result. I'm not showing part 2 because it's taking 27 seconds to compute part 2 in pure Python. Instead, with the just-in-time compilation, it's taking 1 second and a half. So from 27 seconds to 1 second and a half is still a lot of time, but they are a lot of universes. If we want to have an idea of what's going on, this is a graph that shows us what? This graph is showing us, okay, after a round of play, in how many universes are we in a specific configuration? The number of universes is how big the circle is, and those are points for player 1 and points for player 2. So we know that there will be probably only 1 universe here where the point is 8 for player 1 and 2 for player 2, and so on. Every time there is a new iteration, there are more and more universes, more or less in a specific configuration. Just see that with my input, there is never something in this line. So player 2 has never 4 points for some reason. In the end, the number of universe will gradually become less and less, because the one above 20 will be discarded, because when you arrive to 21, the universe is discarded because you have a winner. So it will disappear.
You are converging to 21, basically.
Yeah, you are converging up there. And that is the visualization of what's going on. I also did this with the GPU. This was super tricky because here we have growing and shrinking arrays, and the GPU is not super friendly to handle all of this. So this code is a mess, but I didn't find a way to make it cleaner. We can still see some of the original structure. So there is player 1, player 2, and the else is appending to the list. Yes. But then this list is a fixed size, and I have to pack it, removing the empty universes that I left around. It's a little bit complicated, all of this. Interesting, there is a possibility of doing reduce functions in CUDA. So a sum reduce is taking A and B and is doing the sum. The only point that CUDA is complaining about when doing this, it is complaining here, is that at one point you will have two numbers to put together, and that can't be done in parallel because you only have two numbers. If you sum all the right with all the left, and then you have to put the numbers together, at one point you will have a grid of size 1 because you have to do the last computation at one point. GPU and JITted give the same answer. Okay, so the part 2 in GPU is correct. The JITted version is taking 1.3 seconds, again, as before. The GPU version is taking 0.08. So from the 20 seconds of the pure Python we started with, we went down to 0.08. That is, again, 200 and something times faster.
That's pretty impressive.
Yeah, I have to say that the time to write the Python code was N. The time to write the GPU code, having the Python solution working, was probably 10 times more in writing code. So writing the code that works on GPU, look at all these structures, that has to go back and forth, allocated to the device, or allocated only in the device, is a mess. So if I took 1 hour to write the pure Python solution, and I took 0 to go to the JITted version because it was just adding a decorator, it took me 10 hours to write the GPU version of this. Then yes, it's super faster, but it takes a lot of effort. If you have to do something a lot of times, it makes sense. If you have to do this once, doesn't make sense.
Yeah, it's just an exercise, but it's
just an exercise. It's better to wait 27 seconds than taking 10 hours to write the algorithm.
Yep. Cool. If you have a task that takes you 1 hour, a developer is going to spend 10 days optimizing, automating it. Okay, let's switch to the Rust version and let's try to tell the difference. So basically,
getting attacked.
we have a guest. Nice. We definitely need to do a pet cam.
My God, he's going to write code, guys.
Probably better than my code. Okay.
Catwalk.
So part 2, what do we do? The parsing is exactly the same. So this code is literally copy-paste as before. Then we create the 2 players. This is exactly the same. Then we create a game as player 1 and player 2. And then we have victories, which is an array with 2 positions. And it's basically the number of times player 1 and player 2 are winning, respectively. Then we have this vector of games where basically...
like mine, I was keeping a list of games. You are probably taking the same. And that size is probably the number of universe that game exists in.
I think so. I think we did something very similar. Let's read the explanation.
Okay, guys, we didn't talk about this one, about any of them when we wrote them. So it's impressive.
At every turn, every time we roll a die, we split the universe in 3. Every universe will represent a different outcome of rolling the 3 die, 1, 2, or 3. Because we have to roll the die 3 times, we end up with 27 universes after every turn. The total of a turn is the sum of the 3 dice. This means that the total can vary between 3 worst score to 9 best score. The following table encodes all the possible scores. This is exactly what you did, 3 to 9. And how many chances do they have to happen? 3 and 9 only once, because that means you roll either 1 3 times or either 3 3 times, which can happen only once. 6 will happen 7 times per turn. By doing this, we can reduce the number of simulation to do, because we don't need to run all the 27 simulation per turn, but we can just run the 7 different cases. We will then have to multiply the outcome of every case to how many times that case will repeat. So yes, we did exactly the same thing. So basically, while there are games to play, the current game and the weight, so weight is basically how many times.
And I call it weight too, so this is curious.
So what do? We do games.pop.unwrap. So basically, we take one game to simulate from the list, and is over is initially false. And for victories, either mute enumerate. What was victories?
Is the number of victories for player 1 and player 2, but because I wrote the code twice, you are looping on top of that.
Oh yeah, so for every
every player, is the player 01, 01, 01.
So this will go 01, 01, 01. So player 1, player 2. If the current player has won part 2, then victory plus the weight. So basically,
and this is why it must be either mute, because you are mutating victory.
Exactly. And then
is over. Universe is over.
Equal true, and then we break. If it's over, we continue, which means we take the next one. And then what do we do? If the current game is not over, keep splitting it. So basically what we do is we
add games to the games list.
Exactly. So what we do is for every existing game, pretty much.
Yeah, if the universe we are in is not going to have a winner, we go to the next 27 universes that are born from this, cloning the game, playing the turn of all the players,
and pushing it to the stack of games.
And pushing it to the weight multiplied the new weight, because the new weight is the one from the universe.
Yeah, and then the thing that I do, I take the victories ether.max, so basically I take the biggest value between the two and I wrap.
Yeah.
So
we did exactly the same.
I think that's it. Do we want to run the benchmarks just to compare?
Yeah, I'm curious just to have an idea, because pure Python 27 second, 1.5 the JITted version, and 0.086 the GPU one. That, by the way, took a lot of time to write, so it's not trivial.
Okay, so this is running.
Just to get an idea, do you remember how long it took to you to write this?
Rust, you mean? Oh, what's going on here?
What's happening? You're debugging?
I think I clicked the bug by mistake. Sorry. Let me stop this.
Okay, we want to debug assembly directly, or
no?
For this one, you want to cry in a corner, or?
I definitely don't want to do that. So CD year 2021, exercise 20, right? No, 21.
21 we are. Let's try again. Don't debug, please.
I think that the debugger somehow is still running.
Yeah, it's up there. I see it up there.
Oh, yeah.
Part one, okay. Part one is just a stupid game. I don't even wrote, I think, the JITted version of that. Or probably I did, but okay. Okay, then we can go to take a coffee.
Yeah. Yeah, this is probably not that fast.
My cat wants a coffee.
No. But one thing we never do is to see if we can do things with threads.
Doing parallel thread stuff in Rust. Do Rust provide stuff like Go, Go procedures? Go functions?
I think there are libraries for that. Well, there is a single
okay.
But...
It's not in the language itself.
No, I think there used to be like green... Yeah, there used to be green threads in, I think, earlier version of Rust in the standard library. Then I think they kind of decided it's better to keep it outside. So 600 milliseconds.
In average. So it means that you are still double as fast as the JITted Python, exactly like exercise 20. So if you take the JITted Python and we slice in half, is more what we got with Rust. Obviously, it's lower than the GPU that was 86 milliseconds.
Yep. So,
but we are not we are single core here, right?
We are single core. Yes, we are running everything in one thread. While we could be running, I suppose, every simulation on its own.
Yeah, every bunch of simulation. What I did for the GPU was exactly that one. I allocated 500 blocks, so let's say 512 workers, and every worker was working on a bunch of universes. So you take the whole array, you divide by how many workers do you have. The last one can have a little bit less work because it can be that he has nothing. Or when you are below the number of workers that you have, you will have workers that have nothing to do. That is fine. And then the workers take a bunch of universe and give back 20, at most 27 times, 49 times more universes than the input ones. And then like this. So you have a pool of worker, you can do a lot of universe in parallel.
Yeah, one of the things we should try to do in Rust is that one. And maybe using libraries, maybe looking at whatever are the native features.
Yeah.
Cool. Okay, so I think we should call it a day for today.
I think so.
So let's wrap up.
Okay, so let's wrap up. You can find the recording on YouTube. The link is in the Twitch in the about is on Twitch in the about session. If you're watching this on YouTube, we do live streaming on Twitch every Monday at 6 p.m. Dublin time. That now is 5 p.m. UTC, I think, with the current daylight saving. Make sure to check the Twitch link in the YouTube description and give us a follow and so on, so you can follow us. Feel free to leave comments and pull requests. The repository with the code is in the chat, and in the chat you can also find the YouTube channel at the moment. Perfect. Everything is well accepted. We're trying to learn Rust, so don't expect our solution to be the cleanest or more idiomatic ones. If you know better ways of doing stuff, please let us know with pull request. Thank you for the suggestion, collaboration, the chats, for keeping us company. And are we going to write somebody, Luciano?
Yes, so we are going to be writing Christoph, who is doing Zig language. So if you want to switch from Rust to Zig, that sounds like an interesting channel to follow.
So thank you, bye, and see you next time.
Bye-bye, everyone.